Hello everybody. When you watch a video or movie through various platforms such as YouTube or Netflix, you may suffer from these severe artifacts including false contour or blurred detail. Why do these artifacts happen? The answer is quantization. It will be very grateful if we can remove those artifacts and recover details. So we suggest the deep learning based approach, arbitrary bitwise coefficient for de-quantization, aka ABCD. To summarize our proposal, we propose the implicit neural representation to bit depth expansion by defining proper coordinates and corresponding signals. Furthermore, we insert the phasor estimator to relieve the spectral bias. As a result, we achieve state-of-the-art performance with single training via INR. Quantization is an inevitable process when we convert analog image to digital image. However, some bit service situations such as codec quantize image severely drives the aforementioned artifacts, which is very irritating. Bit depth expansion, or BDE, is a task that recovers these distortions, and the existing learning-based BDE network requires multiple times of training. Before we start the detailed algorithm, let me briefly introduce the implicit neural representation as known as INR. Our ABCD is based on INR. INR takes coordinate as input and overfits it to specific signals such as SDF, video, or image, which make the INR as the function. As its unique concept, it always includes the issue known as the Pearson optimization. To tackle this problem, various works attach the encoder and forward the latent vector as an auxiliary input to INR. This is known as the local implicit representation. But still, there is a spectral bias that induces the network towards the low-frequency components. In this moment, we can consider two problems that we have. First, how to define a coordinate and corresponding signal to bit depth expansion. Second, how to mitigate the spectral bias. The answer to first question is bitwise coefficient. Let's suppose there is an arbitrary positive number a. Then we can represent a to power series of 2, and it can be separated into two terms based on specific integer L. With a simple presimple or infinite geometric series, the second term is abbreviated as follows. If we consider all b are 1, then c must be 1 too. From now on, we call this c as the coefficient. Now we have the following question. Coefficient of what? The c is coefficient of bitwise basis. Suppose that there is a finite field f2 composed with 0, 1, and XOR and multiplication operation. Then 0, 1 to n over the finite field f is defined as the binary vector space that exists the orthonormal basis. When we realize this basis to this term number, it is equivalent to 2 to n minus q. For example, E4 in 0, 1 to 8 is equivalent to 2 to n 8 minus 4. Let's apply them to image quantization. The quantization is same as representing MSBs of image, which can be calculated as following floor operation. As a result, we divide the high bit depth image IN to low bit depth image IQ and residual image IR. R is loss of the quantization operation. We apply aforementioned bitwise coefficients and bitwise basis to reformulate residual image R. Thus, our ABCD is a function of bitwise basis and latent vector Z. To mitigate spectral bias, we inspired by a novel super-resolution INR local texture estimator as known as LTE. Unlike the super-resolution text, BDE only handles the same resolution image. Thus, all of the local coordinate delta will be 0. Thus, we can estimate dominant phase which is dependent on given quantized image. Here's the overall architecture of our ABCD. We use three kinds of modulated encoder, EDSR, RDN, ground truth coefficients, and retrieve overall image with long connection. The result of our ABCD is remarkable. Regardless of choosing the base encoder, we achieve state-of-the-art performance with single training. Let's observe how does ABCD reconstruct 3-bit image. As we can observe, our model removed the false contour in the sky better than the other baselines, also small-scaled false contours in the genes. Furthermore, the ABCD recovered the blurred details in the feather. Let me introduce the another comparison in bit depth expansion. As you can see, feathers, Anna, and Guy, and dogs. Overall, our architecture removed the false contour and recovered the blurred details. Moreover, by using the advantage of implicit function representation, ABCD can predict out of distribution labels. As you can see, only ABCD can remove artifacts effectively. Note that 2-bit image is out of distribution for all methods. However, thanks to implicit function, our ABCD reconstruct unseen labels that includes very severe quantization. Furthermore, ABCD is relatively lighter than the other baselines in the aspect of the parameters and flops. This graph represents that our ABCD overcome the trade-off between PSNR and flops. Also, if we made the smaller size of our ABCD, it still outperformed the baselines. Thank you for watching my video. If you have interested in my work, please visit our paper and GitHub through the QR code open. And meet me in the Tuesday PM session and poster session. Our poster number is 167. Again, thanks for watching my video.